So let me start with an example that we are all aware, I guess, the Sudoku. So in Sudoku you have an input that is made of a grid, and the grid, every cell is either a given clue between a number between 1 and 9, or it's a missing value that we have to fill in. And the rules of the Sudoku says that we cannot have a duplicate in every row, we cannot have a duplicate in every column, and we cannot have a duplicate in every sub block. Now, in ASP Chef, the input and the output must be arrays of models, and every model is an array of terms. This input is obviously not in this format, and then this you can recognize from the errors we are getting, but you can activate this encode, and now everything is put in the input is actually base 64 encoded, so that the ASP engine can understand it, can parse it. Now, we don't want to take the content in this format. Actually, we want to parse a comma separated value that is encoded in this predicate, and we want to produce some output predicate. And in this case, it's going to produce one instance of cell for every row, because we are saying that the separator is the tab. Actually here we used space, so let me change this, and now you see that we produce a more detailed output, one for every cell in the input. Now what we do in this case, we want to remove the cells that we have to guess actually. So maybe we want to say that we have a given clue in a row column with a given value. If we have cell, and the cell has a row, a column, and a value, and maybe you see here that we produce new atoms, new terms, and actually the value must be in the range 1, 9. Down, you have here the given. If you want, you can select just the given predicate, and then the other is going to be projected out. And what other we can do, we can for example show the result as a table, and in the table, if you want, you can also add one or more sorting criteria, and you see that now we sorted according to this first argument, and the same ordering you will have obviously in the output, because every ingredient has an input and an output that obeys to the same format. Yeah, let me remove this ingredient for now. Let's say that we want actually to have a graph representation of this instance, so let's add the graph ingredient. The graph ingredient actually takes a graph encoded in a predicate. Let me use the G predicate to save some time, where we are going to specify the graph. The easiest way is to add another search models, and in this one we are going to specify the nodes, for example. Okay, so we have a node with an ID row call whenever we have given row call with a value, for example. And then if you want, you can also say something more about this node, like it has a label that is the value. And obviously you must separate these terms by comma. Good. You can say more, okay? You can say that the graph has some defaults. The default we are interested in is the node shape. We expect them to be squares. You can say they have a radius that by default is 10. And then you can say that these nodes are not in some random position, but they actually have a fixed x coordinate that is going to be the column multiplied by 20, that it's the double of the radius. And similarly for the row, we are going to fix the y coordinate in this way. Now you see that this is going to match the input. You can have more property in the graph, like you can change the color, say it's green if it's a given clue. Good. So what about the solution of the Sudoku? The solution of the Sudoku, if you want, you can modify this search model, or if you want to keep this, you can add a search model below. So let's modify this one, and now without wasting too much time, I have in my notes a possible encoding of Sudoku. We are going to guess a value for every cell, we are going to satisfy the given clue, we are going to discard duplicates in every block, and the blocks can be row, columns or sub blocks. You can also ask for two models with the rise error option active. This is going to check that there is no a second model actually. And now the solution, if you move down, it should be somewhere here. Obviously you can always remember, you can always select the predicates you are interested in at the end and have just this in the output. And if you want to show in the graph, how can we do this? Yeah, we can have a rule similar to this one, but in this case we are going to use assign row call value. If not given, we are going to have the same representation, but maybe we are going to put a different color like red. Okay, now the green are those that are in the given instance, and the red are those that have been computed by the ASP engine. And if you want to do more, maybe you may want to have this representation for the output. If you look for comma separated value, you see that there is not just parse, but there is also comma separated value, generate comma separated value. This is going to work in the opposite of parse comma separated value. So you start with an input predicate that will be triples, representing the comma separated values, and then you're going to use this separator and encode the result with this predicate. Where you are going to use to specify this guy? Yeah, search model. It will be cell row call value if assign row call value. Now you see that if you decode the output, you have the comma separated value in there. You can change the separator. Yeah, let's use one that makes sense. And you can select the predicates you are interested, maybe just the one encoding the comma separated value. If you also observe it here, the URL changed over the time when we were moving the ingredients, modifying them and so on. You can send this to your friends and then they will find exactly the same solution you have, because everything is run locally in the browser. Here is another example that I want to show. It's Billy the Kids from a programming contest of a few years ago. And in this problem you have a graph that represents cities and connection between cities. You have to put your guards in a minimum number of cities, such that for every path of a given length, for example 3, at least one of the selected city is in the path. And for example, in this input, you see that if we select towns number 3 and number 4, whatever path of length 3 you are going to take here, you are going to hit at least one of these two towns. And these paths are without duplicates. Now, how to solve this problem with ASP Chef? You may start with the input, then you may want to say that this connected predicate is actually symmetric, so you can do this with this module. That actually it's going to encode an ASP program in this predicate, you can observe it's here. It's just these two rules, but that's one way to do in a compact way. And after that, maybe a natural solution for this problem is to have a program that will compute one path of the given length and then ask for all the paths this form. So we are going to use the search model ingredient, and here I'm going to reuse something that I have in my notes. Intuitively we have a starting town, and then we are going to add the next town, and so on until we reach the total number we are interested in. We don't want duplicates. It was a requirement of the program. And then this other predicate in path, it's just going to project the path on the town. And now you see here we have one model that it's going to use to visit the town 1, 2 and 3. And you can search, you can ask for more models and so on. You can ask for all of them in this way. You have to disable the rise error because there is more than 0 models in this case. You see that we have 22 models. Now if I select the input predicate, you may observe that we have some duplicate, like this 1, 2, 3. It's going to appear multiple times, and maybe it would be very nice if we can project them and have just the unique answers. Now for doing this, there is a unique operation that is going to remove duplicates, but remember that the order matters in this case. So before doing this, you may want to add a sort canonical. This is going to sort all the models according to their natural ordering. After this operation, you may want to add the unique, and now you see that we drop from 22 models to just 9 models. Now technically we also lost a lot of information. We lost all the information about the graph essentially, so maybe you want to keep this information, but obviously now this unique doesn't work anymore because it works on all the predicates, but you can exclude some of them. So let me exclude everything with the exception of input, and now you see that we have only 9 unique model according to this predicate. What we do at this point? Okay, now we have still 9 models, but we want to reason on them in a uniform way. To do this, we have the merge operation that essentially will map the models in a single model by introducing an index argument that will be an identifier for the model. Now that you have the model in this format, you can search for more models, and for example you can use this program that will essentially keep track of the path with their identifier, the index of the model, and we can also take the town and the connections, the graph essentially, and this is unique in every original model, so we don't need to keep the identifier. Now you see that we have only one model in output that contains everything we need. In particular, it contains the information about the path, and if you want you can select just the predicates that make sense, these last 4. At this point maybe you want to solve an optimization problem, so let's add an optimize ingredient. How we are going to optimize the search? You can do in this way. So you select non-deterministically a town. Actually you're going to minimize the number of selected town, and a feasible solution is described by these 2 rules. So you are going to say that a path is okay if it contains at least one of the city that one of the town that we selected, and it's not possible for a path to be not okay. Now you see that we found actually one model. It contains the 2 towns that were described in the web page, containing the sample instance. And if you want, you can even draw a graph. Now to draw a graph, you know that you have to encode the graph with a predicate. Let's use the G predicate, and according to my notes, it can be drawn in this way. So here is the nodes. Here are those that have been selected. We use a different color, and we add undirected links for every connected towns. And then you can, if you want, you can also highlight a path. For example, in this case is the number 6, but you can also say the number 4 and so on. Or if you really want, you can also add a slider. A slider is essentially a way to encode a predicate that you find here, slider. This is going to be changed in this way. Actually, we want to change this predicate, so let me put highlight path, and if you want, you can also say the minimum and the maximum you can take from the path predicate. And now if you change this, we are going to display all the 9 paths that we computed, and you can verify that in each of them you actually hit at least one of the selected towns. Finally, if the solution you want to provide to the user is just the number of selected towns, you can have a show directive like this one, and then this is going to be the result of your problem. By the way, let me also introduce the headless mode. Essentially, after you have a recipe, you can hit the headless endpoint with the same representation of the recipe, and you see that all the user interface is hidden, and you just get at the end the solution you are interested in. As a last example, we can consider the context of digital twins, for example those representing a smart building. Here we have a small instance where we have a central building that has 4 floors. Each floor has a few rooms, and the rooms can be equipped or not with sensors to derive the temperature value, or maybe the fact that the room is occupied or free, the fact that the light in a floor is on or off, and so on and so on. Now, this stuff can be queried with ASP Chef. In the query, usually you want to have also embedded a proper visualization of the answer. So, for example, here we have that the input is represented as a comma separated value, and then you can query to select all the devices and have a representation in this way. We can see here that in the graph we not just simply represent the connection, but we can also include different colors for representing the fact that a floor has the light turned off or on, or maybe the temperature is below a given threshold. And if you want, you can stack multiple queries. Like in this case, we are selecting rooms that have a temperature below a given threshold, and together with them all the connected rooms. And if you want, you can restrict the query to just the first floor, and this will be the result. You see, everything is really reactive thanks to Svelte, and the output can also be given in terms of simple strings.